Welcome to This Explainer. Today, we're diving into one of the most mind-bending, high-stakes operations in heavy industrial engineering. We're tackling a massive mechanical mystery, breaking down the exact, step-by-step process of vertical equipment erection. If you've ever driven past a massive petrochemical plant or a refinery, you've seen those towering steel columns, right? And you've probably wondered how they even got up there. Well, today you're going to find out exactly how it happens.
So let's just jump right into this. I want you to picture a gigantic, heavy metal tower. It's fully built, ready to go, but right now it's resting completely flat on the dirt, or maybe on a set of transport trailers. Your job, and the job of an entire team of highly skilled structural and mechanical engineers, is to take this behemoth, transition it from entirely horizontal to completely vertical, and stand it perfectly straight up. It's an operation that leaves absolutely zero room for error. To truly grasp the gravity of this, just consider this number, 500. We're frequently talking about lifting equipment that weighs 500 tons or more. That is over 1,000,000 pounds of solid steel. You can't just hook a chain to it and yank it upwards. If you try that, the metal buckles, the cranes collapse, and the results are, well, catastrophic. The sheer scale dictates that this has to be a hyper-calculated mechanical ballet.
Section 1. The Towering Challenge, Understanding the Scale.
In the plant construction industry, this process is officially known as equipment erection. If you're new to this, you can just think of it as the ultimate final assembly stage. It's the highly precise mechanical process of lifting, orienting, and permanently securing massive industrial components onto their designated concrete foundations. It's that critical moment a piece of equipment goes from just being a transported good to a permanent, functional part of an industrial facility.
The ultimate goal is to get this towering, incredibly heavy vertical column sitting securely on its concrete foundation base, perfectly aligned. That is what a successful erection operation looks like. But actually getting it to this safe, upright position, that requires fighting some really intense fundamental physics.
Section 2. Anatomy of a lift, the physics of heavy rigging.
Before anything even leaves the ground, everything, and I mean absolutely everything, revolves around one critical engineering concept: the center of gravity, or COG. The COG dictates every single movement during a heavy lift. If you don't know exactly where that center of gravity is, and you attach your rigging slings in the wrong place, the second that equipment lifts off the ground, it's going to violently tilt, swing, or even flip right over.
Engineers take this incredibly seriously. They calculate the exact balance point during the engineering phase, and then physically paint the letters COG along with a target symbol right onto the steel of the horizontal equipment. Rigging teams use this precise mark to attach their heavy lifting slings. It's the only way to ensure the load remains perfectly controlled and balanced when it goes airborne.
Section 3. The upending process, a delicate mechanical dance.
You can't just pick it up from the top because the bottom will drag and completely destroy the foundation. Instead, it requires a carefully choreographed sequence. Step 1, a massive main crane attaches to the top. Step 2, a highly maneuverable tail crane attaches to the bottom. And Step 3, they lift synchronously.
It is a seriously tense mechanical dance. The main crane slowly hoists the top half high into the air, taking on the massive weight. Simultaneously, the tail crane lifts the bottom just enough to keep it off the ground. The tail crane then moves forward in perfect synchronization with the main crane to prevent any wild, destructive swinging. Slowly, the tail crane feeds the bottom of the equipment underneath the top until the entire structure is suspended completely vertically in midair.
Section 4. Threading the steel needle, the ultimate precision landing.
Down on the ground, the civil engineering team has embedded a massive ring of heavy-duty steel anchor bolts straight into the concrete foundation. The suspended equipment hovering above has a base plate with pre-drilled holes, and every single one of those holes must align exactly with these bolts.
To really put this into perspective, landing this equipment is quite literally like threading a needle while holding a 500-ton bowling ball up in the air. The crane operator is battling the wind, the microscopic sway of the crane boom, and the immense weight of the load itself. Yet, they have to lower it with millimeter precision so the base slides flawlessly over those anchor bolts without bending or snapping them.
It's a crazy contrast between the terrifying, massive scale of the overall towering structure and the delicate, microscopic reality of the touchdown. This is where the crane operator and the ground team communicate through precise hand signals and radios.
They physically guide the multi-ton equipment, often actually pushing it by hand in those final few inches to achieve a millimeter-perfect landing over the foundation anchor bolts.
Section 5. Perfecting the verticality, fighting gravity and angles.
Now, once it's down, we have to clarify a really critical distinction in construction engineering: leveling versus plumbness. Leveling deals with the horizontal plane. You use thin pieces of metal called shim plates to ensure the base plate sits completely flat on the concrete without any rocking. But for a vertical tower, we are far more concerned with plumbness, which means true verticality. This is ensuring the entire length of the tower stands perfectly straight up at an exact 90-degree angle to the earth.
So why are engineers so incredibly obsessed with verticality checks? It comes down to geometry. Because of how angles project over a long distance, even a single millimeter of tilt at the base, literally a gap so small you can barely slide a piece of paper into it, translates into dangerous feet of swaying at the very top of a 100-foot tower. If a tower leans, its center of gravity shifts, placing uneven catastrophic stress on those foundation bolts we just talked about.
Section 6. The final lockdown. Securing the structure.
Once that true verticality is confirmed 100%, the rigging crew aggressively torques massive steel nuts onto the anchor bolts. They use specialized hydraulic torque wrenches to apply exact calculated rotational force, permanently clamping the base plate down. A bit later, the remaining gap under the plate is filled with a high-strength concrete mixture called grout, locking the whole setup perfectly in place.
This lockdown phase is absolutely non-negotiable because of what comes next. Once the crane finally releases its grip, this newly secured foundation will have to fight off incredible external forces every single day of its lifespan. We're talking massive wind loads trying to push over its high surface area, unpredictable seismic loads from shifting earth, and extreme internal operating weights once pipes are attached and the whole thing fills up with heavy industrial fluids. Which leaves us with a final thought to chew on. The next time you drive past a massive industrial tower, don't just see a static piece of metal. Look down at the base and ask yourself, how much invisible force is constantly trying to push it over? It really makes you appreciate the intense, calculated, almost impossible balancing act of the equipment erection that keeps it standing tall. Thanks so much for joining me on this explainer, and keep looking up.